Um, well, my name is Aldo Rodriguez-Puebla, so I'm a faculty member of the Institute of Astronomy at the NAM, and it's a pleasure to be here, as every year. Okay, so I will talk about this paper that we just published this year, but before going into that, I would like to show you some work that we've been doing in our group. So the first thing that I want to show you is this paper published by our student, James Keikos, and the idea is to understand what are the dark matter halos of star-forming and quiescent galaxies. So we know that the stellar-to-halo mass relation is a very tight relation. And I'm going to focus mostly on massive galaxies, galaxies with the stellar masses above 10 to the 10. It has a scatter between 0.15, 0.2 dex. So the question here is, what is driving the scatter around this stellar-to-halo mass relation? So there is this very interesting figure in the universe machine paper where the authors are plotting here the ratio of the stellar mass of quenched galaxies, the mean of the stellar mass of quiescent galaxies, star-forming galaxies, as a function of the halo mass. And what you're seeing here is that if they have the same relation, they will line up in the line that is equal to 1. So below that line, quiescent galaxies have lower stellar masses, and above that line, quiescent galaxies have higher masses. Okay, so at this point, this figure is very important because it tells you a lot about how galaxies are populating dark matter halos. So if you're above the line, the question is, what is driving the clustering in this, with this relation? So what you will then infer is that halo assembly bias is playing a big role in driving the clustering of quiescent and star-forming galaxies, of central galaxies. So if you are below this line, mostly the clustering of central galaxies is driven by the halo mass. So we test this. So the idea is to infer what is the clustering within this plane, a specific star formation versus a stellar mass, in different part, for a fixed stellar mass in different parts of this plane. So what we found, it was very surprising. So what you're seeing here is the autocorrelation function of central galaxies. We are proving different stellar masses and different levels of specific star formation rate. So you don't see any difference in their autocorrelations. And what I'm showing here is only central galaxies. So this was surprising. It doesn't seem that halo assembly bias is reflected in this plot. So then what we thought is, well, let's try to see if we can infer the halo masses of these galaxies using cross-correlation. So what we did, and what you're going to see in the next plot, is that we fix a stellar mass. We select galaxies according to their specific star formation rate. So in central galaxies, and cross-correlate with all the satellites of the same stellar mass. In that way, you can see that the shaded areas that are here is the region where you are changing from the 1 to the 2 halo term. And as you are seeing, so we are, as you go to the top to the bottom, the halo mass should increase if the 1 halo term is increasing. That's one interpretation. So the main, yeah. And also we tested models that had built halo assembly bias. So we use concentration models and accretion models. The concentration was correlated with the specific star formation rate. You can ask me later about the details. But what we see is that halos driven by halo assembly bias models, they were not able to reproduce the cross-correlation functions that I'm showing here. Only those models are based on halo mass. And the implication of that is that we have a strong segregation in the stellar-to-halo mass relation, which I'm plotting here, halo mass in the y-axis, stellar mass in the x-axis, and in the direction that for a fixed stellar mass, quiescent galaxies should live in more massive dark matter halos. The other two panels show the effect of halo assembly bias, which has the relation backwards. Also, we are trying to understand if the galaxy-halo connection depends on environment. You can see the poster by my student, Daniel Salazar. So essentially, he already told you that the stellar-to-halo mass relation, to a good degree, it doesn't depend on halo assembly with environment. You can talk to him about this. So we have another work about whether the specific star formation rate depends on the structural properties of galaxies at a fixed stellar mass. So here, this is a very interesting figure. So what I'm showing here is, again, the distance to the main sequence, the half-life radius, and the different panels are the stellar masses. And we are color coding by the color gradients. So redder colors are bluer centers, blue colors are redder centers. So what you're seeing is that small galaxies have bluer centers, while large galaxies have redder centers. This means that most of the star formation rate in large galaxies is in the outskirts. So what is interesting here is that for a fixed size, you're seeing that there is a population of compact galaxies, are quiescent, of course, but these are consistent with the properties of the star-forming galaxies that have bluer centers. So if we move to this next slide, we are now color coding by the CERSIC index. And you are seeing here that the same galaxies that are quiescent have the same morphological properties that the galaxies that are in the star-forming sequence. The difference is that they have bluer centers. Now, what is interesting, and it's very encouraging for me seeing this plot, is that the strong segregation in the color with the color gradient. And it's in the sense that we should expect. Galaxies with bluer outskirts have larger sizes. They are increasing their size. Galaxies with bluer centers, they are shrinking or keeping their sizes smaller. So color gradients can tell us a lot about how galaxies evolve around the size-mass relation. I will skip these two. And also we have another project about dwarf galaxies based on manga observations. So you can see here these two papers. I'm not so expert on this, but this is our sample. It's mostly galaxies with masses below 10 to the 9, very nearby galaxies. This was an ancillary program from the manga survey, and we have also photometry from this. You can see the details later, or you can ask me. The important point that I would like to show here is that we have spatially resolved data, so we can compute gradients in these galaxies. So one of the interesting things that I want to highlight here is that we are computing profiles of light-weighted edges and mass-weighted edges, as well as metallicity. So these are not, what we are seeing here is that while light-weighted edges profiles, they have a negative gradient, mass-weighted edge profiles have a slightly positive gradients. And you can talk to me more about this later. And also, it is not easy, it is not trivial to compute gradients in dwarfs. So the paper that is cited below, we discuss a lot how to compute gradients and how much uncertainty you can introduce by computing gradients. And at some point, where there are some methods that will give you essentially that there are not gradients, and some methods that will tell you that there are negative gradients. Okay, so after that, I'm going to what is my real talk about this paper that we published. So the galaxy's Dark mass function is one of our key quantities to understand how galaxies are growing in time. Essentially, if galaxies are growing only in mass, they will move in this way, since the galaxy's Dark mass function has a lower amplitude at higher redshift. So the way that we figure out how to understand galaxies move around with the galaxy's Dark mass function was in a very simple way. So there is this cumulative number density matching in which you pick up, what I'm showing here now, it's the cumulative galaxy mass function and the stellar mass here. So you fix one number density, and you are connecting points here to the same number density, and that will give you a curved growth of the stellar mass. So that is the simple way to understand how galaxies are growing in the stellar mass function. However, this is very unrealistic assumption, as we are assuming that galaxies are maintaining rank order in this figure, and it doesn't account for stochastic processes, and it's also biased due to observational bias, that is Eddington bias. So here's an interesting figure about random errors and how do we understand Eddington bias. So what I'm plotting here, it's the 1 sigma that is being reported in these papers of the errors in calculations of stellar masses as a function of redshift. So as we go to higher redshift, these errors increases. So if you don't take into account these random errors, it's a bit slow. if you don't take into account those random errors, you will use these solid lines to track your constant number density, as I showed before. But if you account for random errors, you should use now this dashed line. So see how much difference we have here after accounting random. Oops. Sorry. After accounting random errors. This is something that we should take into account. Sorry. Here I'm giving you a very simple prescription of how you can deconvolve your galaxy star mass functions for those random errors. So this is something that you will infer if you are not accounting from random errors. So sorry, now I backwards the lines, but now the dotted line is using the observed galaxy stellar mass function, and the solid lines are now what I'm calling the true or accounting for the random errors in the galaxy stellar mass function. So we will infer lower stellar masses as we go in the past because of the Eddington bias. However, this is not the only correction. That was the most simplistic correction that we should do. So there are other corrections and caveats that people have pointed out to this. So there is this paper by Peter Beruzzi where he provided a very simple recipe for how galaxies should evolve around number densities, but he did it based on his semi-empirical model. Now there are other papers that can be used also hydro simulations to give recipes to connect galaxies. So let me tell you that we can rethink this problem in a very simple way. So how about understanding how halos are growing? We don't need to enter into much detail if this is just a simple prescription to understand how galaxies are growing in time. So what I'm plotting here is the median assembly history of dark matter halos with a variable that is proportional to redshift. So the solid lines that I'm showing here are fits to the, the dotted lines that I'm showing here are fits to the simulations, and the solid lines are simulations based on from inferences from the Bolshoi-Planck and the multi-dark Planck simulations. So what I'm going to do is to use these median assembly histories of dark matter halos and evolve it around the halo mass function. So what you are seeing here is now the number densities for the progenitors of these dark matter halos are redshift 0, and you are seeing how the number density is evolving as a function of redshift. The dashed line that I'm showing here is the recipe provided in the paper by Peter Beruzzi for comparison. So you are seeing that the slopes depends on the mass at redshift 0 of your progenitor. So high mass halos will have a steeper slope, while lower mass halos will have a more shallower slope, although the lowest mass will have a slightly steeper slope. This is another way to see it. So we have different redshifts for the halo mass function, as you see here. And this is at the moment that I started the dark matter halos. So they are increasing in this way their number densities. Okay, and this is now examples for progenitors starting at redshift 2 and progenitors starting at redshift 0, also compared with a recipe given by Peter Beruzzi for comparison. So now, how about using those tracks and the idea of subhalo abundance matching to walk through the evolution of the galaxy stellar mass function with their number densities and infer the growth of galaxies? So, well, it says here M beer, which is the cumulative number density of halos. You are supposed to say that this is also the cumulative number of galaxies, of stellar mass in galaxies, if the connection is provided by abundance matching. So this is a very complicated figure, but let me go to this figure and walk through it. So here, the dotted lines is the traditional method introduced, I think, by Van Dokkum, in which you are matching the number density of the observed galaxy's mass function. The solid line is the new method that we are saying that you can use the evolutionary tracks of the dark matter halos, and the dashed line is a recipe provided by Peter Beruzzi. So with this very simple model, you can infer very realistic of what we believe are the median evolutionary tracks of dark matter halos. By the way, so there is this GitHub where you can download the code and you can reproduce all those figures that I've been showing. And this is a project that we call Concha. Concha in Spanish is, in English is shell. So this is like a sweet bread in Mexico that is very famous and everybody loves them. So we decided to call it Concha. Okay, so what are the implications for the things that we are doing? What I'm showing here is the stellar mass divided by the baryonic mass, which is the universal baryon fraction by, times the halo mass as a function of redshift. So we are seeing the evolutionary tracks of our galaxies. So if you use only those cumulative tracks based on the Van der Kolk technique, which are these dashed lines, you will infer that at higher redshifts, galaxies will have higher star formation efficiencies. While if you use the tracks that we are providing, you will infer more conservative star formation efficiencies for those galaxies. And also, and this is perhaps a takeaway for people that is trying to compare galaxies with dark matter halos at higher redshifts, and that you shouldn't forget about Eddington bias, how Eddington bias is working. So what I'm showing here is the evolutionary track of a halo with the mass that is shown on the top and at redshift 5. So this is the median that we should infer, right? Now, this dotted white line, dot-dashed white lines that I'm showing here is the intrinsic scatter around the stellar to halo mass relation. So essentially, this will be the tracks of all the galaxies that will evolve to those masses. But if you start to add in quadrature, and perhaps this is a very simplistic way to think about this, but if you start to add in quadrature random errors based on the figure that I showed before, and I will come back to that figure, you start to see that there are observed galaxies that are above of the universal baryon fraction, which is the violet line that I'm showing on the top. The same thing is showing here. So there will be an important fraction of galaxies that we will infer that they have higher baryonic fractions of what we expect at those redshifts. I'm coming back again to my figure of random errors as a function of redshift. And in the previous figure, I showed you the results of using this relation that I'm showing here in the upper envelope for random errors. But there is new data, in particular here there are random errors estimated based on James Webb data, which tell us that maybe at higher redshifts they are not so pessimistic like these random errors. So what we decided to do is to define this region as our region of uncertainty. I don't necessarily should believe that these are correct because they look more or less the same random errors at redshift 0, but we decided to be more conservative by having this area here. Even though, if you do the difference between the true galaxy stellar mass function, which is the one deconvolved by random errors, and the observed galaxy stellar mass function, which I'm showing here, the difference in log, and this area that I'm showing here is the same area that is showing here, you will see that at very high redshifts, the differences between these two quantities could be between 2 and 3 orders of magnitude. So it's very important to take into account those. In addition, if you put the intrinsic scatter of the stellar to halo mass relation, you will have larger differences. So it's very important when you compare to higher redshifts, it's very important to take into account Eddington biases. And finally, we also provide a way to generalize this model. So we use the model, the halo mass growth histories proposed by Risa Weschler as a way to modify a bit our fit of the growth of dark matter halos. So now our formula for the median growing of our dark matter halos will depend on a formation time. So you can use whatever you think that halo property is parameterizing that halo formation time. So now you can infer not only the tracks for all the median track for all the halos, but tracks for early and late forming dark matter halos. That will be reflected into into tracks between what we could say are quiescent and star-forming galaxies based on some fraction of formation times. And I think I did it one time. And this is my summary. And I will take questions.
One quick question for Aldo. Yeah.
Hey, this is fantastic, and I really love the detailed treatment of errors. I think I wanted to ask, so there's studies that do star formation histories from individual galaxies from things like SET fitting, and you can bin them up in a mass and redshift bin to get like the average history for a population. Have you compared like what you get from this to those histories, and do they agree?
Right. So one of the questions is, so if we compute the slopes around this region with time steps that we believe that we are proving with the star formation rates, like 100 megayears based on UV or 10 megayears with H alpha. So what you get here is really a Gaussian, very close to a Gaussian distribution of 0.3 dex width. We haven't compared directly, but it's very close to that.
Thanks.